Parker, and we're here to teach you about calculus with the help of...
me, Tina Fey!
Today's lesson is on tangent lines and the correct usage of the first derivative test.
Does anyone know what a tangent line is? Yes, Marcus? Exactly!
Good for you!
That is good. Thanks for that, Tina. I believe you have a wonderful presentation of just that. Right, Craig?
Right!
I got it! A man here is riding on the surf. We set f of x as the curve of the wave. Observe the slope of the surfboard. The trace of the slope is the derivative of f of x.
So, what happens when the slope of the tangent is equal to 0?
I'm glad you brought that up, Paulie, because that brings us to our next lesson.
Oh, you mean maximums and minimums? Yeah, let's cover that. Caroline, is that a cell phone? If you don't put that away right now, I'm going to personally take it and throw it out the window. No, I don't give a hoot. Put it away. Thank you. So where was I?
I know. We were about to explain the first derivative test before you were rudely interrupted.
Right. Alright, everyone take out your calculators. I'm going to show you a really cool trick. Let's say we have a function x squared plus 4x. And when we graph that, we get the curve. But if we want to find the derivative at the point x equals 2, we hit second, calc, dy dx. 2 equals 8. So, anyways, to find the local maximum and minimum of a function, all you need to use is the first derivative test.
Right. The first derivative test uses...
Wait, I got this. The first derivative test uses the first derivative of a function to determine whether a given critical point is a local maximum, a local minimum, or neither.
Wow, Tina, that's actually correct.
Right, a critical point is when the derivative of a function is equal to 0 or undefined. Can't forget that. Yes, Bobby? Do you have something you'd like to add to the lesson? No, you cannot go to the bathroom. You had all day to go to the bathroom, and you think you can interrupt my lesson just to go to the bathroom? Are you kidding me? I know you're sorry. Don't let it happen again.
Here. Let's do an example.
Yeah, let's do that. Craig, take a breather. Here, we have an example of a cubic function. Tina, take it away.
Alright, so here we have a function x cubed plus 3x squared minus 9x minus 13. When you take the derivative, you get f prime of x equals 3x squared plus 6x minus 9. You can factor it out, a 3, to get 3 times the quantity x squared plus 2x minus 3. And then you can factor it even further and set the equation equal to 0 to get 0 equals 3 times x plus 3 times x minus 1. You set these to 0 individually to get 0 equals x plus 3 and 0 equals x minus 1. You end up with x equals negative 3 and x equals 1. You put these numbers on a number line. You take a number that is less than negative 3 and plug it into the derivative. In this case, you get a positive. Then you take a number between negative 3 and 1 and plug it into the derivative. In this case, you get a negative. Then you take a number greater than 1 and you plug it into the derivative. In this case, you get a positive. If you look over here, it's a drawing of what this graph would look like. It goes increasing to negative 3, decreasing to 1, and increasing further. You plug in negative 3 and 1 into the original equation, which has been knocked down, and then you find out the points. From the drawing, you are able to see that at x equals -3, there's a maximum, and at x equals 1, there's a minimum. So then, you take -3 and 1 and plug it back into the original equation and to see what the points are of the actual maximum and minimum. When you plug in -3, you get 14, so you know the maximum is at -3, 14. And when you plug in 1, you get -18, so you know the minimum is 1, -18. Booyah!
So, here we have a function, f of x equals x cubed minus 9x squared plus 27x. So, when we take the derivative of that function, we get f prime of x equals 3x squared minus 18x plus 27. So now we set the derivative to 0 because we're looking for critical values, and critical values occur when the derivative is 0. So we get 3 times x squared minus 6x plus 9, and we can factor that even further and find out that 3 times x minus 3 times x minus 3 equals 0. So obviously x equals 3. When we put 3 on the number line and plug in a number less than 3, it's increasing, but when we plug a number greater than 3, it's also increasing. So, I'm over here now. Well, so if you look at the graph of the function, you can see that the function is always increasing no matter what. So, we know that the critical point is 3, 27, plug it into this equation right here, but we know that there's no min or max. Booyah!
Don't forget, class, all maximums and minimums are critical points, but not all critical points are maximums and minimums.
Alright, so here we have another example. F of x equals sine x plus cosine x. When we take the derivative of that function, we get f prime of x equals cosine x minus sine x. So, set it to 0 because we're looking for the critical points. And we get 0 equals cosine x minus sine x. So, sine x equals cosine x, obviously. Then when you solve for x, you get x equals pi over 4 and x equals 5 pi over 4. Okay, so now we're going to put those two values on the number line. When we plug in a number less than pi over 4, we get a positive, so it's increasing. And then when we plug in something between pi over 4 and 5 pi over 4, it's negative, so it's decreasing. And now we're going to plug something greater than 5 pi over 4, but still in the domain of 0 to 2 pi, and we'll get positive again, so it's increasing. But since it's on a certain interval, we have to plug in the endpoints. And when we get the endpoints, we get 0, 1, and 2 pi 1. Now, poof, I'm over here now. So we crossed out the endpoint values 0, 1, and 2 pi 1 because although sometimes endpoints can be maximums or minimums, not in this case because 1 is less than root 2, which was the value at pi over 4, and it's also greater than negative root 2, which was the value at 5 pi over 4. So we know these two values right here are our maximum and our minimum. Booyah!
Peekaboo! Evan, I see you. And to the rest of the class, goodbye and thanks for coming. Well, have a nice day.